Physics students, good afternoon. Mr. Fugit here. In this video today, we're going to be looking at the idea of electrostatic force, the interaction between charged particles. Specifically, we're going to be looking at problem 3 on homework number 12, which is the square problem, where we have 4 different charges set up in a square pattern. So our problem statement reads like this. Four point charges, each of magnitude, my value is 11.02 microcoulombs, are placed at the corners of a square 77.5 centimeters on a side. Now, when I hear that, I'm going to go ahead and draw that picture because we're not given a picture directly here, and it's important for us to have it. So, we have 4 point charges arranged in a square pattern, like so. We're told that the square is 77.5 centimeters on either side. So I'll just go ahead and write that on one side so that we can see it as such. Now we're told this. If 3 of the charges are positive and 1 is negative, find the magnitude, how big the force is experienced by the negative charge. Coulomb constant will remain the same, the 8.98 e to the negative 9. So we're told the charge, we'll say positive, 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 negative. Doesn't really matter which point we say is negative. It doesn't matter because it's just asking us for how big the force on that charge would be. So you can call it whichever one's positive and negative that you want. And I'm going to say the negative's in the bottom right corner. So our charge Q is 11.02 microcoulombs, or we do convert it as we will need to, 11.02 e to the negative 6 coulombs. Okay? Now that is true for all of our charges around the square. The distinction we'll need to make is the bottom right charge for what I will say will be negative. Now, as you can guess, because we're dealing with positive and negative charges, there's going to be some attraction forces involved. So before we do any solving mathematically, something that I want you to see, okay, is that all of these positive charges are going to want to pull that negative charge toward itself. So over here to the left, this positive charge is going to want to pull on that negative. And the same thing is going to happen with this charge in the top right. It's going to want to pull that negative charge up. And the same thing is going to happen with this charge at a diagonal. It's going to want to pull this charge up. So our negative charge is going to be experiencing 3 different forces, right? One from the charge to the left, one from the charge straight up, and one from the charge at a diagonal. And it's going to be our job to find out, well, how big are those 3 forces, and then to sum them up like we do when adding the force vectors. Now, in the problem statement, you're going to be given your charge. That's going to be the same for every single point. We're also going to be given a distance that is a straight line from one point to another. So, what I'm going to go ahead and do is I'm going to find we're going to call this F1, this force to the left, F2, this force upward, and F3. I'm going to start with F1 and F2 because they're in one direction, and then we're going to move to F3. So, force 1. Well, we know that we can find this electrostatic force using our equation. K is equal to Q1 times Q2 divided by D squared. Now, we know our Coulomb's constant. I'm going to continue to use the 9 e to the 9th value. Now, we know that the amount of charge involved is always going to remain the same, right? That 11.02 microcoulombs. Okay? We do know, however, that there is one positive and one negative charge in there. So we'll say 11.02 e to the negative 6th and negative 11.02 e to the negative 6th. Those are our values of coulombs. And then we'll divide by the distance between those particles squared. So coming back to our picture, don't forget, we're given that distance. My value is 77.5 centimeters. We'll go ahead and convert that to meters. 0.775 meters, and that value is squared. So let's go ahead and plug in and solve for F1. K, 9e to the 9th, there's our calculator, times 11.02 e to the negative 6th times negative 11.02 e to the negative 6th divided by 0.775 squared. In doing so, I get a value of negative 1.8 will go 2 newtons. Now again, remember, the negative just tells us it's a force of attraction, okay, which we already knew that because there's a positive and a negative charge involved. So this is one of our forces that we're going to need to use later on. Now, I said I was going to solve for F2 next. I'm going to tell you a little shortcut. If you'll notice, when solving for this force, the variables that we factor in are Coulomb constant, K, Q1 and Q2, as well as the distance value. Now, other direction. In this scenario, for F2, our charges, Q1 and Q2, are staying the same. Still a positive 11.02 microcoulomb and a negative 11.02 microcoulomb. We also have the same distance, 77.5 centimeters. We also have the same constant. And therefore, if all of our variables are remaining the same, we know that F1 is also equal to F2. So we don't have to do any solving in that scenario. Excuse me. So there's two parts of our our work already done. Now lastly, I need to solve for F3. So K, Q1, Q2, remember our charges are staying the same here, are 11.02 microcoulombs. The difference here is that our distance is a little bit different than our last couple of scenarios, right? Because we're not dealing with a straight line from one charge to another. Now we're dealing with something at an angle, right? So I'm going to redraw our picture to give us a little bit more context for what's going on. And if this is our negative charge down here in the corner, our positive charge up here on the top left is some distance away. So 77.5 centimeters over and 77.5 centimeters up. Remember from the beginning of the year when we talked through some of those different trigonometry, those principles of trigonometry, we can use here the Pythagorean theorem. Since this is a square, that will be a right angle. So we'll take a squared plus b squared and set that equal to c squared, right? Not c squared, just c, if you will, which is going to be d in our equation. Sorry if that's a little confusing. So a squared, 77.5 squared, plus b squared, again 77.5 squared. We'll add those together and then take a square root. And we'll get a distance of, I get about 109.6 centimeters. So it's going to be the value that we plug into our equation to find F3. So here we go. F3 is K, 9e to the 9th, times 11.02 e to the negative 6th, times negative 11.02 e to the negative 6th, divided by 109.6, which when we convert to meters is 1.096 meters squared. Okay, so we'll go ahead and plug in what we know to solve for F3. So 9e to the 9th times 11.02 e to the negative 6th times negative 11.02 e to the negative 6th divided by 1.096 squared. That seems a little bit high. Oh, I know my mistake. Okay, that number seems a little bit better. Okay? Live action mistake, there you go. So, F3, I get a value of negative 0.9, that's about 0.9, that's tricky to round. Let's go 1. I don't usually like rounding like that, but we'll go with that. Negative 0.91 newtons. Now remember, the negative just tells us it's a force of attraction, which means it's going to be pulling the negative toward the positive. Okay? So now that we have all of our forces, it's our job to sum them up to find the one overall force acting on that negative charge. So I'm going to redraw my picture to simplify things out a little bit. So here's our charge, Q. And it's negative 11.02 microcoulombs. Now we have three forces acting on that charge. F1, F2, and F3. Now, we know F1 and F2 are the same value. That was the negative 1.82. Now, I'm going to drop the negatives off because now the negatives are just telling us about direction. So this is 1.82 newtons left, 1.82 newtons up, and then 0.91 newtons at this angle. Now, what you might be tempted to do is simply add all the numbers together and throw them into your answer box on Quest. And I would remind you, we cannot do that because all of these force vectors are in different directions, meaning we need to find their components and add those together. So, if you'll notice, two of the vectors, the one to the left, which we called F1, and the one straight up, F2, are already in kind of component form. They're already in one direction. The tricky part here is F3, because it's at an angle. So what we need to do is take F3 and break it into its components. So, let's go ahead and do that. I'm going to redraw F3 like so. And it is 0.91 newtons. And we know inherently that there is an x and y component to that force. Now, because we're dealing with a square, the diagonal is going to split that right angle, meaning this angle here is going to be 45 degrees. So if we use one of our trig properties, really doesn't matter which one, we have our hypotenuse, we're looking for one of our other sides. So let's say we use the sine function. So let's go sine 45 is opposite, that would be our y component, over the hypotenuse, 0.91 newtons. And I can multiply the 0.91 over, so that my y component is 0.91 sine of 45 degrees. Okay, so we'll take our value, multiply by 0.191 sine of 45, and that's going to give me a y component of about 0.643 newtons. So that is the y component of F3. Now, because we're dealing with a 45, 45, 90 triangle, because we're dealing with a 45, 45, 90 triangle, we know our x component and our y component are going to be the same value. So we know that the y value of this force and the x value of this force are thus the same, 0.643 newtons. So now that we've broken F3 into its components, we can add everything accordingly. Okay? So in the x direction, we have 1.82 newtons. And since F3 is also kind of partially to the left, 0.643 newtons. And in the y direction, we actually have the same thing, right? 1.82 newtons up, what we call positive. And F3 is also partially up, 0.643 newtons. So when adding these together, we're going to get about the same value. Okay? So 0.643 plus 1.82, not 182, is going to give us right at about 2.46 newtons. And what that tells us is that our negative charge experiences a force of 2.46 newtons left and 2.46 newtons up. So now we've redrawn this picture several times, but we're going to do it now for the last time. Here's our negative charge. It experiences a force to the left, 2.46 newtons, and a force upward of 2.46 newtons. And what the question is asking us is for the magnitude of the overall force that our negative charge experiences. Okay? And again, you'll recognize we can use Pythagorean theorem to find that force. So we'll take 2.46 squared plus 2.46 squared, and then we'll take a square root of that value, which will give us right at about 3.48 newtons. Now again, this is asking us for the magnitude of that force. It's not really asking about direction, because remember at the beginning of the problem we can choose any corner that we want to make our negative corner. Okay? So it's really just asking us for the magnitude. How big is that force? And when we check our answer, 3.4785. That's good. I should have checked that before to make sure I was doing it right, but we'll go with that. So, as you're working through this problem, remember, we're not really doing anything brand new. We're still looking at force between charged particles. The difference here is how we sum up those forces at the end, and we have to make sure that we add those forces as vectors. So, hopefully this will get you started on problem 3 in the right direction. Best of luck.